right, the purpose of this video is to solve for a parallel RL circuit, or a circuit with a resistor and an inductor in it. So the first thing we need to figure out, in this case again, is an RL circuit. So on the left hand side you'll see I've got my vector relationship here, and with our vector, we know that the horizontal line represents what is in phase. And in this case, in a parallel circuit, we know that what's in phase, or what is the same in a parallel circuit, is voltage. So with our Eli and ice, we know that the last letter that is E belongs in the word ice. So we have our capacitive current leading, and that's ICE going clockwise, and then ELI. So I have my inductive current lagging, which means that my resultant vector is going to be somewhere over here, because I have an inductor and I have a resistor, so I have both. So what we needed to do, just like we did before and always, is we're going to write down everything that we know. And this question here specifically asks us to determine the apparent power, but what I'm going to do is we're going to solve for everything. That way we know how to solve for everything. So in this case here, we have got a resistor value. I'm going to scratch this stuff off when we write them down. We can see in our question we have a resistance value of 48 ohms. So I'm going to put 48 ohms over here at my resistor. So I'll take that as my resistor value, 48 ohms, and I've got an XL, or inductive reactance, of 130 ohms. So we'll write down our 130 ohms over here, and we'll scratch that off. And I have a source voltage of 239 volts. So here's my 239 volts. Okay, so just like always, and again, we have to use, this isn't like a series circuit where I can use my impedance triangle, because we know that in parallel, my impedance is going to be lower, in this question, is going to be lower than 48 ohms, because it is the lowest ohms value that we have. And just like DC theory, in a series circuit, where my impedance is going to be higher than the highest value, and in parallel, the impedance is going to be lower than the lowest value. So, but what we do have is we have source voltage. You have to use your current triangle in order to solve for parallel circuits. So in order for me to find current, which I don't have two values in one location, but I have 239 volts, because it's parallel and we know that voltage is the same. Okay, so now we can take our calculator, and I'm going to go from right to left. I'm going to do the inductor first, where I have 239 volts and 130 ohms, and that gives me a value. It's 1.838, so we're just going to put 1.84 amps. And I know that that 1.84 amps is right here, 1.84 amps. Now I'm going to take my 239 volts and divide it by my 48 ohms at my resistor, and that's going to give me 4.98 amps. 4.98 amps, because we know that what happens at the resistor always is on the horizontal line. Okay, so now I've got my 4.98. Now I just have Pythagoras, right? Pythagorean theorem. So I'm going to take the square root of 4.98 squared plus 1.84 squared, and that's going to give me a total current of 5.31 amps. So 5.31 amps. And now I can solve for my impedance. So I'm going to take my 239 volts and divide it by that answer, and I'm going to get an impedance of 45.02 ohms. And we can do this 100 times out of 100. All right, so we can solve. And now for P, we're going to multiply up here in a second, but what I want to do is I want to take a split second, and I want to say that there is an alternative way to solve for impedance. So I'm going to slide this picture up just a little bit. And just with my ohms values, I can solve for my impedance by what is called the product vector sum method. Product vector sum method is taking R, and now my computer's wanting to wait a second, so takes your R times X, in this case it's XL, divided by the square root of R squared plus XL squared. Now you don't have to do this technique. You can do the way we did it by solving your currents, solving your total current, dividing source voltage by total current, and getting your impedance. This is just an alternative way to solve for impedance, step one. Okay, so I'm going to take my R of 48, multiply it by 130, and divide that by the square root of 48 squared plus 130 squared. And when I hit equal, I got a value of 45.03 ohms. So we can do it that way, but again, you don't have to do it that way. So let's go ahead and scroll this back down. And like we said, we're going to go ahead and multiply up and get our p values. So I'm going to take my let me put in 5.31 first. I'm going to use the 5.31 value, multiply by 239 volts for source. And that gives me 1269.09. I'm going to take my 239 and multiply it by 4.98, and that gives me a value of 1190.22. And I'll take my 239 and multiply it by 1.84, and that's going to give me a value of 439. 0.76. And now if we take those values for P, we can take our our true power, 1190.22, and put that on our horizontal, the 439.76, and put it on our vertical. And then we could do A squared plus B squared equals C squared. We should get 1296.09, because we can also use our power triangle when we do this. So the only things that we have to solve for now that we haven't solved for already is power factor and phase angle. So for my power factor and phase angle, power factor is the cosine of theta, and theta is that angle right there. That's not a very good curve. So, but power factor is, on our pig sheets, if you have a pig sheet, power factor we can solve for in parallel. We can either do watts over voltamps. We can always do watts over voltamps. Series, parallel, doesn't matter. We can always do watts divided by voltamps. True power over apparent power. In this case here, we can also do one of two ways. We can do resistive current, and that's the one I'm going to do right now. Resistive current, 4.98, and I'm going to divide that by my total current, which is 5.31. And when I take my 4.98 divided by 5.31, I get a power factor of basically 93.8%. I could have also done Z, my impedance, 45.02, divided by R, 48, because they are inversely proportional, ohms and amps, right? So I could have taken Z divided by R, which is R divided by Z in series, but I could have done Z divided by R in parallel, or like I said, and what we did, or what I did, was IR divided by IT. All right, so that gives you a power factor. It presents on the calculator as 0.937853107, but I'm going to take that value, I'm going to leave it in the calculator as that, and I'm going to do the inverse cosine of that value to give me my phase angle of 20.31 degrees. 20.31 degrees. So what that means, because I have an inductor and my voltage sine wave is going to cross zero going in the positive or negative direction, 20.31 degrees before the current sine wave is going to do that. So the voltage is going to lead by 20.31 degrees.